All right, welcome everybody. So let me introduce today's speaker, Josue Nassar. He has been working in my lab as a PhD student since 2018. He's done really great work, published in top machine learning conferences such as ICLR and NeurIPS. He has been a force in the lab, pushing many different projects. And this particular project that he will talk about today really started very early on. So it's been a while since it has been perfected, and we're about to release it to the world. So you're going to see a sneak peek of the great work of Josue. He's not only a great researcher, he's also very positive, and he's great personality. So I'm sure most of you who know Josue will agree with me that he's a great positive influence in his circle. Anyways, with this, I'll let Josue take the floor.
Thank you, boss man. Okay. All right, so let's get started. So hi everyone, and thanks to the boss man for the introduction. And so we'll go over the talk, which is titled Maximizing Exploration in Unknown Dynamical Environments with Potential Attractors. And before I continue, I think it's super important that I give acknowledgements now. So of course, I want to thank everyone in the Catnip Lab. And specifically, I want to give a big shout out to three people. One, Yuan, Ian, and of course, the boss man, Memming. And also another shout out to two of my friends and collaborators. One of them, Kendall Lowry, another one, Benjamin Evans. They helped me a lot when I first started learning reinforcement learning, and this project wouldn't have been done without them. Okay, so exploring an unknown environment is critical for an agent to be successful. So this is something that biological agents have been doing for millions of years. So here we have a video on the left of a cute little hamster trying to escape jail. And it's moving around and it's finding its way, and it's going to escape. And so, although biological agents can do this pretty easily, this is something that has been troubling artificial agents for a while now. And this is because it usually takes artificial agents millions of time steps to explore even somewhat adequately. And so because of this, a bunch of fields have done research and exploration. So one area of, science and engineering that deals with this is SLAM. So here, SLAM stands for simultaneous localization and mapping. And so here, the problem is you put an unknown agent, which is usually a robot in a building, and the goal is for the agent to explore and build a floor plan. Another area where exploration is super important is reinforcement learning. So here we have an artificial agent playing Montezuma's Revenge, which is a popular Atari game, popular in the RL community. And it's been known for decades that exploration is crucial for reinforcement learning, because for an agent to find a good policy, it needs to explore. And actually, this game remained unsolved, and it wasn't until research and exploration that allowed an artificial agent to beat this game. And so exploration becomes much more harder in dynamical environments, as we can see here with this squirrel kind of getting caught between these rotating things. And it's much harder in this setting because now the agent has to deal with and potentially leverage the autonomous dynamics of the world, as you can see in the video. And this becomes much more harder in environments with attractors. So here, this green ball, you can view it as the agent. And it's much harder because in these environments, right, the dynamics are designed to keep the agent stuck in these Bayesian of attractions, which you can view as these troughs. And so, of course, I'm in Memming's lab. We all care about neuroscience. So you're probably wondering, why does the neuroscience care about attractor dynamics? But attractor dynamics are actually ubiquitous in neuroscience. So for example, so in theoretical neuroscience, dynamical systems, and especially attractor dynamics, are a useful tool for explaining neural computation. So here, as you can see on this vector field here, this is a theoretical model of decision making. So assume that some monkey or animal has to choose between left or right. You see that here that we have two stable fixed points, which is denoted by these black dots here. And you can think of each of these stable fixed points as corresponding to either a left choice or a right choice. Whenever you have an agent performing some sort of stereographed periodic motion, for example, like walking, running, it's usually very, very prominent that you'll find limit cycles in neural data. So here, for example, is this figure from Russo et al., where they recorded neurons from motor cortex while a monkey is pedaling a wheel. And as you can see here, right, these traces that were found from the neural data all basically line up on the same limit cycle, the same sinusoidal thing, oscillatory thing. Metastable and multi-stable attractors are also pretty prominent in neuroscience as well. So here we have the study from Hudson et al. And what they did is they examined the latent state or the cognitive state of a human while it's going through different levels of anesthesia. And what they found is that as the human is recovering, it visits these different hubs, where each of these hubs correspond to metastable or stable states. And of course, these are just 3 examples. There are a ton of examples in neuroscience where dynamics and attractor dynamics are everywhere. And so if we had an algorithm that could explore these dynamical environments, then we can start doing a bunch of cool things. So one important application of exploration is system identification. So here on the left, we have the true vector field or the true dynamics. And here the X corresponds to the state of the brain, for instance, or it could be anything. And on the right, we have some learning algorithm. It doesn't really matter what it is. But you can see, right, that the agent is only visiting this top limit cycle. And so if you look at this picture on the right, it learns a good estimation of this top limit cycle, but since it's never seen the bottom one, it's never going to learn it. And so what this means is that we're only getting a partial view of the dynamics. But if we had an algorithm that could perturb this, then we can get a much more global view. And this is useful because now we can learn more things about neurocomputation. Clinically, exploration is also pretty amazingly too. So here, in our lab, one thing that we're interested in is escaping diseased neural states. So here you can view this purple dot as the latent or cognitive state of the brain. And here you can see that it's trapped in this attractor on the left. And that attractor can represent some neural disease or cognitive disorder. So as you can see here, we're viewing this as the coma state. And so ideally what you want is you want this purple state to go over to the healthier attractor, which here corresponds to a higher level of awareness. And so you can pose this as an exploration problem because efficiently exploring, by doing that as a byproduct, you're going to visit other attractors. And so if you had an exploration algorithm that could do this, you can leverage measured electrical activity and you can choose things like stimulation frequency, stimulation amplitude, etc. Okay, so now let's dive into a more concrete definition of the problem. So here we're going to let x of t be the state of the agent at time t. So here you can look at this little robot. And the spatial temporal evolution of this agent is defined by f. And f takes in 2 inputs, the previous state of the agent at time t minus 1 and the control u of t. And we also allow for the possibility of some state noise epsilon t. Now, the important thing about this problem is that the agent has no control over the dynamics, right? The agent can't change the laws of gravity. So if the agent wants to interact with the world, it has to do it by choosing these controls u of t. And so the goal is you want to choose a sequence of controls that allows you to efficiently explore the potentially dynamical environment. So as I mentioned earlier, exploration is super hard. It's been unsolved for decades. And so we're going to use this cartoon to help us realize why it's so hard. So here we have a pirate out at sea, and this crow took its map. Now, of course, like any good pirate, this pirate is obviously distressed. So now if the pirate wants to reach its destination, it has to explore the sea. And as you can see, it's a pretty dangerous sea, right? We have some tornado, a whirlpool, this like weird Kraken thing, this Loch Ness monster, volcanoes. But thankfully, this is a good story, and we have the pirate, the pirate reaches the island and gets his treasure. But if we really start to analyze this comic, we can really see why exploration is so hard. So as you can see, the pirate lost its map, and this represents the pirate has minimal to no knowledge about the environment, right? So the only way that it can learn about the environment is with repeated interactions. The second thing is there is no reward signal from the environment, right? The sea is not telling the pirate where to go. The sea isn't telling the pirate where it's been. So it's up to the pirate to keep track of this intrinsically, and through some mechanism, it has to have some intrinsic reward signal that helps drive or direct its exploration. The next thing is that the environment is dynamical, right? I mean, like I said before, we have these whirlpools and these tornadoes and these weird monsters, and this makes exploration much more harder. If in contrast, the sea was a calm day and these monsters were somewhere else, it'd be much more easier for the pirate to explore. And lastly, and what I want to argue is the most important thing is this exploration is done completely online, right? The pirate can't just like, if it ends up going to, I don't know, here, it can't just reset itself to some arbitrary state, right? Moreover, there's only one pirate, right? You don't have multiple copies of the pirate exploring the sea in parallel. And so, as I mentioned earlier, exploration has been a pretty important thing in reinforcement learning because in reinforcement learning, it's been well known that if you want to get better at a task, which is encoded by this reward signal RFT, then exploration is crucial for finding a good policy. And so for decades, the de facto method for exploration is epsilon greedy. And really, these methods rely on just injecting stochasticity. So you randomly sample some control signals U of t from some distribution. And this has been really popular for a variety of reasons, right? It's really simple to do, very efficient. But as the tasks have gotten more complex and the environments have gotten more complex, researchers have realized that using these methods are too simple, right? And the reason why, it's because it's open loop, right? The control signals that are randomly generated aren't using any feedback from the environment to help choose better ones. So an approach that's been popular, that's gained popularity in the last 5 to 10 years, is reinforcement learning with intrinsic rewards. And so here, what the agent does is it augments the environmental reward signal RFT with some intrinsically generated reward signal IoT. And so in this vein, research has been based on designing IoT, because you want IoT to reflect the agent's exploration efforts. And so we can categorize them under 2 categories. A very popular one has been comp-based rewards. So in this setting, the agent maintains a state visit count. So here on this left figure here, there's 3 states in this environment. And you can see here that the bars represent how many times the agent has visited that state. And the intrinsic reward that it generates is just inversely proportional. So states that have been visited less get rewarded higher, as you can see from this paragraph on the right. And so count-based rewards were originally designed for discrete environments, but they've been extended to continuous environments. And really, the easiest case is you just take a discretization. So here, let all these dots represent all the states that agent has visited. So in this count-based rewards for continuous environments, you just discretize the state, and now you just keep counts over this discretization. And again, your intrinsic reward is just inversely proportional to the state visitation counts. So another very popular form of intrinsic rewards are curiosity-based rewards. And here in this setting, the agent is incentivized to visit states that lead to high surprisal. And so there's basically 2 very popular forms of surprise. So one of them is prediction error. So in this setting, the agent maintains an internal world model, which we're going to denote by F hat. And at every time step, it predicts where it's going to go. And the intrinsic reward signal that it generates is the difference between the true state of the agent at time t and its prediction. And to see why this is a good measure of surprisal, we can have a simple example here. So suppose that this figure on the left is the true vector field, and all these gray dots are training data. We can train our internal world model, which we're going to look at it on the right. And we can take the difference between these 2 vector fields, and this is what this figure here is showing. And as you can see, points that are close to your training data have low surprisal because you visited, which is represented by blue. But the further you go away from it, the larger the surprisal is. And another popular form are uncertainty-based rewards. And here, at a high level, what's done is the agent keeps track of some posterior, which we're going to denote by YT condition on this. And this YT can be anything. It can be the dynamics. It can be the value function. It's not really that important. And so the intrinsic reward that's generated is just the uncertainty of the posterior, which as a proxy, we're going to use variance. So again, if you look at this figure on the right, gray is once again our training data. And so points that are close to the training data have low variance, low uncertainty, while the further you get away, the higher uncertainty gets, so the higher reward is. Right. So as I've mentioned before, right, this is all this research has been done, but there's a caveat, right? So in RL, the goal of exploration isn't to explore the environment, it's just to get better at the task. But in our setting, we're interested in exploring the environment. The task is to explore the environment. And as we saw before, right, there is no environmental reward signal that we can use. So one possibility is the agent can just use the intrinsic reward signal as a means to explore the environment. And this has been explored before in reinforcement learning. So here we have this study from ICLR 2019, where they trained artificial agents using purely curiosity-based rewards. And here their measure of exploration is the number of times that an agent can juggle a ball. And you can see here that training a reinforcement learning agent using purely curiosity-based rewards does lead to exploration, as you can see on this figure here. As the agent gets more and more data, it is able to juggle the ball more and more times. But there are some caveats, right? So the first thing is that most of these methods use model-free RL, and these methods are notoriously sample inefficient. So in the figure that I just showed you, it took the agent on the order of millions of frames to juggle the ball 6 times. The second thing is, in reinforcement learning, the environments that these agents are tested on are usually offline and episodic. But as I mentioned earlier, in the setting that we're interested in, we want to do it online. This is super important for neuroscience because there's only one brain, and you can't reset the brain to some arbitrary state. And the last thing is that all of these intrinsic reward functions that have been proposed in literature are usually somewhat heuristic, and they rely on a deep neural network. And the reason why this is a caveat is because now you have to do an optimization subroutine. You have to hope that you take enough gradient steps for the deep neural network to reflect the agent exploration effort. So here, to see all of these things combined, here is this video. Green is the state of the ball, disregard the red ball. And so here's a state-of-the-art reinforcement learning agent trained using a previously proposed intrinsic reward function. And you can see here that the agent actually just gets stuck in this top corner of the maze. So, and we can let the video keep going, but it's actually never going to escape this. So you can see here, this is empirical evidence that we do need a method that can explore. And mind you, this is not even a dynamical environment. This is just a very simple maze. And so the rest of the talk is going to be focused on us introducing our method. So the first thing we're going to do is we're going to propose a new intrinsic reward function. We're going to couple this intrinsic reward function with a model-based reinforcement learning algorithm. We're going to prove that this leads to a synergistic relationship between the two. And if we follow the map, we'll lead to X marks the spot, and we'll look at our new fancy algorithm called escape the maze. So now here, this is the same environment, but now you can see escape the maze explores much faster, right? The ball moves much faster, it covers much larger swaths of ground. And if we wait a little longer, you see that the escape the maze actually does fully explore this maze. But you'll just have to take my word on it. Okay, so let's get started. So we're gonna go move into part 1. So one intuitive choice for intrinsic reward function is the following. So here, given the state of the agent, which we're going to denote by capital X less than t, suppose the agent visits a new state, which we're going to denote by lowercase x, we can just take the distance, the closest distance from any of the points in memory, which is denoted by this d term here. And if you look at this figure on the right, you can see that here, once again, all these dots correspond to the agent state visitation history. So the closer you are to these points, the lower the reward is, which is denoted by blue. And the further you get away, the higher reward you get. So this form of reward function has a lot of less properties. One, it's very simple and intuitive. Two, it adapts instantaneously, right? So as I mentioned earlier, previous proposed reward functions rely on some deep neural network that needs to be optimized. But here it's pretty straightforward. So suppose the agent visits a new state, which is denoted by this black star. If you want to update a reward function, we just add that point to memory, and now our reward landscape adapts instantaneously. So no optimization subroutines are needed. And one, you can show theoretically that if for our distance function you choose L2, what you can show is that attempting to maximize this intrinsic reward function is equivalent to maximizing some entropy estimator. And this is nice because if the environment is bounded, then the maximum entropy distribution is uniform, which by definition is maximum exploration. But as you can tell, there's a caveat. This method is way too slow. The reason why is because the agent has to keep adding every single state that is visited up until time t. So for super long exploration efforts, this thing will become huge, and now computing this is going to become way too slow. And of course, we can't use this in an online setting. So the first thing we're going to do is we're just going to consolidate. So instead of remembering every single point that we've done, the agent is now going to remember a set of landmarks, which is denoted by this tuple here. So MK is the landmark center. So here in the figure, each of these dots is a landmark center. The BKs are region of interest. So in the figure here, it corresponds to these circles. And each region of interest maintains a visitation count, which is denoted by this N thing there, which is denoted by N1 here. And so here at time t, the agent, once the agent visits a new state, it finds the closest landmark closest to it, which we're going to denote by K star. And then what it does is it just computes the distance to that closest landmark, so which we're going to denote by DK star. So if this distance is less than 1, then we say the agent has visited that landmark. So we can see in the figure on the left, this black star corresponds to the state of the agent. So here we said that the agent has visited this yellow landmark. And so what we would do is we would just increase the visitation count by 1. Now, if the agent visits, so now if the distance from the closest landmark is greater than 1, then now we see the agent has visited, has now entered a new part of the space. And so what we do is we just create a new landmark. So the landmark center just becomes the state of the agent, and now the visitation count of that landmark becomes 1. And so now, given this consolidated state history, we're going to propose the following, which is the reward function. And it's comprised of 2 parts, right? So this part is a count-based approach. So here, this calligraphic BK corresponds to all the landmarks the agent has visited up until time t. And so now, if the agent has visited any of the landmarks, it receives a reward that's inversely proportional to the number of times it's visited that landmark. We also have this term on the right that is the discovery bonus. So here, if the agent creates a new landmark, then it receives a reward that's proportional to the distance to the closest landmark. So as you can see here by this reward landscape on the left, you can see here that the agent is incentivized to visit new landmarks, right? So if you're inside any of these landmarks, then you receive a much less reward if instead you create a new one. And so again, this has a lot of nice properties. Again, it's pretty simple and intuitive, easy to compute. It also adapts instantaneously. So if the agent creates a new landmark, all we have to do is just include that landmark in our consolidated state history, and our reward landscape adapts instantaneously. But now, as we showed for version 1, right, you can show theoretically that maximizing that thing also corresponds to maximizing some form of entropy. So it would be nice if you can show the same thing for this one here. And so to get there, as a byproduct of this consolidated state history, you can view it as some sort of online tessellation scheme, right? So each of these landmarks and visitation count, you can view it as some discrete approximations and discrete PDFs to the state visitation history. And so I won't go into the details here, but actually what we show is that you can prove it. And so the proof is pretty intuitive, so I won't spend too much time on it. But here, suppose that this is the state visitation count. So here you have 3 landmarks, each of them with accounts. So there's 2 cases. One, you either don't create a new landmark. So in this case, the agent would be incentivized to visit landmark 1. So you can see here that now this state distribution is closer to uniform, which is maximum entropy. And the second case is you either create a new landmark, and what we can show is that always creating a new landmark always leads to increase in entropy. And so, as I mentioned in the intro part, there have been count-based rewards, and our reward function is somewhat similar to it, so it's important to discuss the differences. So the first thing is that previous approaches usually use some sort of static discretization scheme. So a priori, they've already defined the width of these boxes, for instance. Where ours is somewhat dynamic, right? The actual location of this tessellation scheme is denoted by the agent. More importantly, though, is that our reward scheme has a notion of distance. So if you were to use a purely count-based approach, right? If you look at this reward landscape here, right? It doesn't matter if the agent creates a landmark here or here, it will be rewarded exactly the same. But that doesn't make any sense. So in our setting, there actually is a notion of distance. So the further you get away from these previous landmarks, the higher you get rewarded. So now that we have our intrinsic reward function, we can now do reinforcement learning. So as you can see from this title, we're obviously going to use model-based, but I think it's super important to discuss why we use a model-based approach in the first place. So let's just quickly review model-free reinforcement learning, or reinforcement learning as a whole. So classic reinforcement learning, right, is to find a policy denoted by pi that maximizes the value function. So the value function takes in the initial state of the agent at time x, and it computes the expected discounted reward. So here, gamma is a discount factor that's less than or equal to 1. And importantly, though, the reward function is purely Markovian, meaning that the value of this reward function depends only on the state of the agent at time t. This is important because if the agent stays in the same part of the space for t and t plus 1, then the magnitude of the reward would be exactly the same. So doing some math, right, we can decompose into 2 terms. And from here, we get the celebrated Bellman equation. And the Bellman equation is super important because virtually every model-free method that's out there relies on this. So reinforced, actor creator, TD learning, Q learning, deep Q learning, all rely on the Bellman equation being true. But remember that our goal is to explore. And exploration is fundamentally non-Markovian, right? So if an agent were to stay in the same place for 2 time steps in a row, you would want the reward function to be less, right? You want to incentivize the agent to visit novel states. So once again, we can look at this modified Bellman equation, which we know by B tilde. Again, we get this similar summation term. We can do a similar decomposition, but now you can see that the Bellman equation no longer holds, right? Because now the value function, the inputs to it has now increased by 1 dimension. And so what this means is that theoretically, all of these popular model-free reinforcement learning methods do not work in this setting. So an alternative is to do a model-based approach. So in model-based reinforcement learning and control, right, these control signals are chosen through planning. So here, this V, we're going to call the predicted value function. So you have a planning horizon H, you have an internal world model, which we denote by F hat. And so here, what the agent does is it takes a sequence of controls and it predicts where it's going to be. And given that predicted trajectory, it computes the intrinsic reward function. Excuse me. So here we have a nice little graphic. So suppose this was the state of the agent. It would take in 3 different control sequences, U1, U2, U3. For each of these, it would predict where it would go. So as you can see here, we have these 3 different red lines. And for each of these 3 different red lines, you would compute the predicted value function and choose the control sequence that would lead to the maximum predicted value function. And so this is nice because we're no longer bound by the Bellman equation, right? So it doesn't matter if our rewards are Markovian or non-Markovian. All that matters is that we can compute this thing here. The caveat is that while in model-free RL, right, the horizon is infinite, in model-based RL, the horizon is usually finite. And the last thing, and is probably one of the most important things, is the sample efficiency. So as I noted earlier, right, model-free methods are notoriously sample efficient, while model-based methods are usually much more sample efficient. So here we have this figure from a study by Brembaugh et al., where they compared model-based and model-free methods on an environment. And you can see here, the model-based methods denoted by blue and green, right? They get pretty decent performance after 2 million frames, while here, all the model-free methods, even after 8 million frames, are nowhere near close to the model-based methods. And this is important because if we want to explore efficiently, we would want a method that's sample efficient. And so given all of these things, we use a model-based method going forward. So now, if you're going to use a model-based method, right, the agent needs an internal world model. And so, as I mentioned earlier, since the agent has no a priori knowledge of the environment, this dynamic world model has to be learned online. And so in the beginning, while the agent is exploring, or when it visits new areas, right, you would expect the estimate there to be really, really bad. So it's important that the agent has some notion of uncertainty, right? So the agent should, when it's doing this planning, it should take into account how certain it is in its dynamics model. And so here, for this, we use a probabilistic model. So practically, we use an ensemble of deep neural networks, but our approach is amenable to anything that you want. So it can either be Bayesian, non-Bayesian, et cetera, as long as there's some notion of uncertainty. Okay, so where are we at? So we have our intrinsic reward function, I of t, right? We're using a model-based approach. And this predicted value function takes us 2 inputs, right? Again, this intrinsic reward function, but also the internal world model that has a notion of uncertainty. So because the goal of the agent is to maximize this thing, it'd be nice if we would know how these 2 things interact, right? How the agent's confidence in the world model interacts with this intrinsic reward function, I of t. So to get there, let's take a very simple thing. Let's only look at myopically. So when the planning horizon is just 1. So here, our predicted value function is the following. We can do some math. I'll skip the details. And we get this following lower bound, right? And this lower bound is comprised of 2 terms. So here, this blue term is the agent's prediction that it will visit a previous landmark. So under its internal world model, what is the probability that it will visit a landmark it's already visited? While the term in green is the agent's prediction, the agent's confidence that it will create a new landmark. We can do something similar and obtain the following upper bound. So again, this upper bound is comprised of 2 terms, right? The blue term, which again is the agent's confidence, its prediction that it will visit a previous landmark. And this term here is the agent's prediction or confidence that it will create a new landmark. So now let's look at the 2 extremes. So on the left, right, the agent is 100% confident that it will visit a new landmark, right? Oh, my bad, that's a little typo there, but it doesn't matter. So this is the agent's confidence that it will visit an old landmark. So you can see that this value function is upper bounded by 1. While on the other side, if the agent is fully confident that it will visit a new landmark, now you can see that this value function is lower bounded by 1. So intuitively, what this means is that if the agent wants to maximize rewards, it wants to find controls that leads to this thing being high. And intuitively, this makes sense, right? So if you're going to an airport and you're going to buy a plane ticket on the fly, right? If you aren't really focusing on anywhere, you'll probably end up somewhere, a part of the world that you've never been before. While if you focus on Europe and you're well traveled in Europe, it's pretty likely, it's much more likely that you'll visit a city that you visited before. And so I've given you an intuitive description, but can we actually show this theoretically? We actually can. So here we have the following theorem. Well, the theorem isn't really important, but the simulation is. So here, this X corresponds to the state of the agent. And here, all of these red dots are just trajectories, so predictions. So you can see here, each of these green circles are 3 landmarks. So as the uncertainty as the uncertainty in the world model increases, right, the probability of the agent will create a new landmark increases as well. And you can see this figure on the right. This also leads to an increase in the predicted value function. And so this is nice because now this leads to a synergistic relationship, right? So high uncertainty leads to a much larger predicted reward. So the agent is incentivized to visit areas of state space where the dynamics model is not confident. What this leads to is this leads to learning a much better dynamics world model. So as you can see here, decreases uncertainty. And what this does is now you have a much better dynamic world model, which now leads to better planning. So this is nice because, as I mentioned in the beginning, there are 2 forms of intrinsic reward functions, right? Count-based and uncertainty-based. Each of these are separate, but the combination of a count-based reward function and an uncertainty-aware dynamics model gives you 2 for the price of 1. And to our knowledge, this is the first time this has been shown, and I think it's pretty nifty. And so with all of this combined, now we have our algorithm escape the maze. And so here you have an agent in an unknown world. As you can see, it's obviously stressed. And so here at each time point, the agent, the state of the agent is at time t. This state now goes into the dynamics model, updates it, and it's also used to update the landmarks. So now these landmarks give you this intrinsic reward function. And this combined with the dynamics model is, you now do model-based planning or model-based control. And this now gives you a control state of U of t, and this just happens recursively. And so now let's move on to the experiment section to provide empirical evidence that our method actually does do stuff. But of course, it's important for us to do comparison. So here we're going to quickly discuss the baselines. So the trivial baseline is just random control. So the agent just chooses controls randomly in an open loop fashion. We're also going to compare against actor critics trained with TD learning. And so each of these will be trained using the intrinsic reward function. So one of them we're going to use prediction error, which I mentioned earlier. So the agent maintains an internal world model F hat, which is trained online continuously. And so for the uncertainty one, we're going to use random network distillation, which is a very popular one. And so here, the agent maintains 2 deep neural networks. Here, a randomly initialized but fixed one and one that's trained. And under some hand wavy math, you can show that this intrinsic reward function is actually a proxy for predicted variance. So this actually is an uncertainty-based one. And so classically, reinforcement learning assumes that the discount factor is less than 1, so it's discounted. But a lot of work has shown that actually it's usually much better to use a non-discounted version. So we're also going to compare against these non-discounted versions, which are going to denote by a star. And so to ensure that all of these are kosher, we do a baseline optimization scheme to choose the best hyperparameter. So all of these methods are very, very well tuned. In contrast, ETM is not very well tuned. We use pretty simple hyperparameters that are kept across. And so I haven't really discussed how we chose this W term, which basically controls the width of this circle. So there's probably a lot of ways to do this, but we're going to choose a dumb way on purpose. So what we're going to do is for the first 100 time steps, ETM is just going to choose random controls. Then what it's going to do is it's going to compute the covariance, and then it's just going to take that and scale it. And that's the W that's going to be used going forward. Okay, so let's move into some experiments. So the first thing we want to do is we're going to compare these methods on these classic control tasks. So specifically, we're going to compare against 2 of them. So here we have mountain car. So you have an under-actuated car, and the goal of the task is to get this car up the hill to visit this little flag. And we also have Acrobot. So we have a 2 chain link arm. And here the goal is to get the bottom of the R up until this black line here. And we chose these 2 tasks for a variety of reasons. One, they're de facto methods that are usually used to benchmark reinforcement learning implementations. The second thing is both of these have attractor dynamics, right? So here in mountain car, right, there's an attractor at the bottom of this hill. And here for Acrobot, the attractor is just the agent staying still. And 3, each of these methods, right, as a byproduct, if you explore efficiently, you can solve these tasks. So here, if the agent efficiently explores this hill, as the byproduct is going to reach this flag, and again for Acrobot, efficient exploration would lead to the arm visiting the top of this thing. So we compare all of these methods, and as you can see here, first we'll look at mountain car, and you can see here that random control almost never beats it. Mountain car is not a non-trivial task, and some of the model-free methods are able to do it, as you can see here, but ETM is able to do it faster and also much more stably too. As you can see here, a lot of these methods have very high variance, while ETM, the variance is pretty low and does it pretty easily. It also does very well in Acrobot too. So Acrobot is also much easier than mountain car. So you can see here, even random controls can beat it. And again, all of these model-free methods can do it too, and ETM also can do it too, stably and fast. So here, this is as you can see here, our implementations are well. Our hyperparameter optimization scheme is working. So now there's confidence that things are working as expected. So of course, our method is called escape the maze. So we should make sure that it can explore a maze. So here, we're going to look at a ball exploring a maze. So here, the state of the agent is a green ball, and the state space is two-dimensional. So the XY coordinate of the ball and the XY velocities. And the controls are 2D. And we say here that the agent has solved the maze if it's visited all the bins. So the maze is discretized into 26 bins. So again, now you can see a huge difference, right? None of these methods, random controls, nor any of these state-of-the-art model-free methods can explore the maze. While escape the maze can explore this 100% of the time. We can actually view these methods in action. So here on the left, you can see escape the maze. Again, the ball moves much more quickly, covers large swaths of land, and does this, I would argue, somewhat trivially. But if you look at each of these methods, you start seeing something pretty interesting. So for random network distillation, the method is always going to stay in this upper arm. Prediction error was able to move down here, but it's actually never going to leave. It's just going to stay there. And random controls, here, while it's exploring somewhat slow, right? You can see the ball is kind of backtracking and isn't really moving that quickly. We can actually visualize this. So here, the color gradient denotes time. So the red star is the initial position of the agent. So you can see here that for escape the maze, as you saw from the video, explores these large swaths of land, moves very quickly, and you can see the mixing in color, right? So it's even backtracking. Random controls, while it does explore, you can see that the movements are somewhat redundant, right? The agent is kind of circling back to where it's been, and even though it has explored a large part of the maze, it wasn't able to explore it as efficiently. But in contrast, the model-free methods here, R&D, like I said earlier, never escapes this upper arm. And in actuality, random controls performs better than these state-of-the-art model-free methods. Again, you see something similar with prediction error. Again, even though prediction error was able to visit another arm, it basically just stays there. Of course, you can view this across multiple random seeds. So you can see here, you can view the percent of the maze covered over time. And you can see here that escape the maze explores efficiently and always explores the maze. But in contrast, all of these model-free methods saturate, right? There is some initial exploration but they don't really do anything past that, while random controls is better, which is insane. So as I mentioned earlier, we very quickly gloss over a theorem that shows that maximizing our entropy reward function maximizes entropy. So here we can actually provide empirical evidence. So we compute entropy across the discretized bins. And you can see here that the dashed black line is the maximum entropy. And ETM actually does maximize entropy. It does get pretty close. Random controls also does pretty well. But you can see here for all of these model-free methods, there is an initial increase, but then it saturates and actually ends up decreasing. Okay, so let's move on. So now let's move on to a continuous chain environment. So a very popular environment for testing exploration abilities of reinforcement learning agents is a discrete chain environment. So here, the agent is just this green person, and the states are just each of these discrete states. But this is discrete, and our method is the method is targets continuous environment. So here we made a continuous version of it. So now here, each of these bases of attraction corresponds to each of these discrete states in the chain environment. So in the chain environment, the agent can either move left or right or left, while in the continuous chain environment, the controls are continuous. And this makes it much harder because now in the discrete chain environment, random controls allows you to move from state to state, while in the continuous chain environment, trivially applying random controls doesn't really move you from one phase into another. Okay, so some more things. So it's been well known in RL that the initial state of the agent determines the difficulty of the problem. So for the discrete chain environment, the agents are usually always initialized in the leftmost or in the rightmost state. In our setting, what we're going to do is we're always going to initialize the agent in the middle. This is much harder because now for the agent to solve this task, it has to backtrack, right? It has to go all the way to the right, has to realize that it has to backtrack and then go all the way to the left. And to make the problem even harder, we're now going to embed this 1D dynamical system in 2D. So here you can see that the attractors are all on this line. And this is important because now the agent has to realize that it can only explore in this 1D space, that the other space is basically not informative. And we also add noise to make things even harder. So now let's look at how all these methods perform as a function of chain length. So just to make sure we're all on the same page, here we're going to look at a chain of length 3. So here, right, the height of the bar denotes the number of times the agent was able to complete the task. So here you can see that random controls never beats the task. R&D probably beat it 1 out of 10 times, while all of these methods never did. While here, this dashed black line represents 100% success. And you can see here that ETM is able to do it 100% of the time. So now we can now view this as a function of chain length. And you can see now that ETM always solves this regardless of chain length. Random controls never solves it. And all of these state-of-the-art model-free methods solve it somewhat sporadically, but isn't stable, right? So you can see here that R&D solves it somewhat sporadically, but doesn't do it. The non-discounted version never does it. And prediction error does it a little better, but still not stable. So now what we can do is we can actually view the completion time. So the number of time it takes for the agents to visit all of the chain lengths. So the dashed red line represents failure. So if you see something up here, it means that it wasn't able to do it. So ETM, as you saw from the figure before, is able to solve the task pretty easily and also scales pretty gracefully with chain length. While again, as you saw from the previous slide, all of these state-of-the-art methods aren't able to do it. So now we can actually view this in action, right? So again, remember the first 100 time steps, ETM just takes random controls. That's why you saw in the beginning, which is kind of randomly jittering. ETM is able to go all the way to the left. Well, if you look at all of these methods, right, random controls never escapes. Random number distillation is going to start moving and prediction error too. But what you'll see is that prediction error and random number distillation basically get to the left and never leaves. We can wait a little longer to see this. So R&D takes a little longer. Well, if you're noticing, ETM has already solved the task. It's already visited everywhere. And now it's just retracing its steps. Here on the right, you can view entropy as a function of time. Again, the dashed black line is maximum entropy. And ETM gets really close. While, as you can see for all these model-free methods, they basically end up, there isn't an initial increase and they just end up saturating. So now we can view this phenomenon over chain lengths and over random seeds. So here, ETM, the slope of this line is 1. So regardless of the chain length, ETM will always visit all the chains. But if you look at the slope of these model-free methods, it's about 1/2. And what that means is that each of these methods are able to get to one side, either all the way to the right or all the way to the left, but isn't able to backtrack. And again, as we showed before, we can view the similar entropy argument. So we can view it over multiple seeds. And again, you can see the ETM is able to maximize entropy and does get pretty close, while all of these state-of-the-art model-free methods just end up somewhat saturating. Now, lastly, we can move to a much harder example. So we're going to look at ant maze. And so it's been well known in the RL literature. This method is notoriously hard, right? So the state space is 29-dimensional because you have to keep track of all of the actuators on this robot, on this ant. The controls are 18 and continuous. And so here, again, we're going to compare all of these methods and see how it does. But the space is 29 dimensions. And so I've kind of swept this under the rug, but our method really only works well in somewhat low D space. And so to make our method amenable, we're going to compare two things. So the first thing is that we're going to take this 29-dimensional vector and just randomly, so keep the first two, the XY coordinates, and just randomly down project the other 27 dimensions. And we're going to keep landmarks in this 8D space. The second thing is we're only going to keep landmarks in the X and Y coordinate and just completely forget about the other 27 dimensions. So now we can view these in actions. And you can see here, as I said earlier, this task is super hard, very, very, very hard. And although all these model-free methods never do it, ETM, the 8D version, is able to do it 40% of the time, and the 2D version is only able to do it 20% of the time, sadly. So, but we can, start looking a little closer. So we can look at again, the percent of the maze covered as a function of time. And even though ETM, the 2 versions, doesn't always solve the task, we can see that it does explore a lot better than these model-free methods and purely random controls. So we can once again visualize this. So here we have a trial where ETM did solve. So you can see here the red star denotes the initial position. And you can see here the ETM moves pretty efficiently and actually has started to backtrack. While if you look at these model-free methods, R&D, prediction error, and their non-discounted versions, they seem to move in the beginning and just seem to get stuck. So again, as you saw in the previous maze example, they aren't really adapted well for exploration. And while the 2D version of ETM in this one seed that we chose, it does do initial exploration, but again, just seems to get stuck and doesn't really move anywhere. So we can look at each of these over multiple random seeds, right? Because we want to know why ETM isn't solving the task, right? Maybe it's something to do with ETM, maybe it has something to do with the task itself. So you can view here over all of these 5 random seeds, right? ETM is exploring. So it isn't that it's doing bad. It's just that there's so much to explore that it's just taking a long time. So in hindsight, I probably should have ran this for longer, but which I will do. But so at least here we're confident that ETM is doing the right thing. ETM is well suited for this task. We just have to let it run for longer. While in the 2D version, ETM in some instances it does do well, right? This is one seed where it did solve it. And it is exploring in these, but in some of these, you can view that there's these large clusters, right? So it's exploring, but somewhat redundantly. But if you remember, this actually does make sense, right? So as I showed you previously, there's a synergy between learning the model and the landmarks, right? But what we're saying here in this 2D version is that you don't care about the uncertainty in 27 dimensions. So from a model learning perspective, that's pretty important because those 27 dimensions are going to be important for forecasting. And so to conclude the talk, so in here we introduced Escape the Maze, this model-based control algorithm that's designed for exploration and online exploration. So there's a lot of cool things. One, as I just said, it's well suited for this online non-episodic task. And so here we've already shown theoretically and empirically that it is able to explore these continuous environments using a very simple reward function and a very simple uncertainty-aware dynamics model. This method is also fast, right? So one of our target applications is applying this clinically. And if you want to do that, you do need fast. You obviously do need it to be fast. And so the nice thing about this method is that the dynamics model is plug and play, right? So we've been able to get speed up to 100 Hertz using just random Fourier features. And you can also get to 10 Hertz if you want to use a really brolic neural network. So it's up to the practitioner for them to choose the trade-off between expressivity and fastness. And again, as we've just shown empirically, we can escape all of these really weird attractors and we can just dominate in all of these super cool environments. And so, of course, I want to thank the lab, the Catnip lab, the current members and the former members, all of my collaborators and friends who have decided to work with me and all my crazy ideas over the years, and all of our funding sources. And thank you all for sitting down listening to me talk for, I don't know how long I've been talking for. Thank you. Any questions, comments, or concerns? Let them fly.
Maybe I can jump in with a quick question. So this is multiple elements of your talk and your problem really struck a similarity with me with the problem of optimizing the structure of a large molecule. So you imagine a large floppy molecule, you can bend it and stretch it and twist it in all sorts of different ways. And a classic example is a cluster of small water molecules, right? Tiny little molecule. And basically, even if you just think about the relative positions and orientations, you can end up, even with a small cluster, with trillions of different minima, of which one is the global minimum. And so I wonder, what's the connection between, well, you're solving a hard problem. What's the connection between this problem and the global minimum problem?
Right, yeah. I mean, so one useful thing about this method is, so if you were to apply it so you can view each of these local minima, I guess in our case, is attractors. So as a byproduct, ideally, if you'd apply this method in that setting, I would like to think that it would find the global minima quickly. But the important thing is that it does have to be augmented, right? I mean, so here in this setting, I kind of swept under the rug, but the method just keeps on exploring, right? The agent never knows when it's done. It's always doing it. So if you were to apply it in a setting like that, you would need, the practitioner would need to have, I don't know, some sort of flag or something that says, okay, you've reached a global minima, or you've reached something which I think is a global minima, and you can stop there. So, but I would like to think that this would be much faster than, for example, zeroth order optimization, for instance, where you just randomly go over all of these local minima. I
know there's a method, it's fairly old now, called umbrella sampling, that's used to explore these configuration spaces. And again, it's based on some ideas in maximum entropy, but of course it's so old it predates machine learning concepts. So are you aware of that? Is there any connection?
Umbrella sample, is it the same thing as simulated annealing?
It's related, yeah.
What's the difference? I mean, I can talk about simulated annealing, but I don't know if I remember what umbrella.
Yeah, I can't. I'll put a link in the chat, and then just the ubiquitous Wikipedia page. There's lots more out there.
Yeah, I mean, so I can quickly mention like simulated annealing if that's helpful. But
yeah.
I mean, I would still consider simulated annealing to be like, simulated annealing to me is still like somewhat reminiscent of epsilon greedy, right? So I mean, there is still open loop, right? So like in simulated annealing, you do need a sequence of temperatures. And I mean, choosing those temperatures is highly non-trivial, right? Like I know in the MCMC literature, if you want to use these annealing type methods, then finding those sequence depends on all of these constants that you don't know about. And so while you can do it, I would still view it as a very open loop method.
Super cool. Thanks. I really enjoyed it. Thank you.
Thank you.
Jose, there's a question in the chat.
Oh, well.
Yeah, as the musician, I was intrigued by your word expressivity. So can you talk a little bit more about that?
Expressivity. Oh, yeah. So, wait, let me just go back to the slide so I can. So I spoke about it here. Right. So here there's a trade-off, right? So the agent or the practitioner, I guess the practitioner is the agent, has to choose what's the parametric form of the internal world model, right? Which is this F hat term that comes in this slide. And so there's a lot of choices that you can choose. So for things like a deep neural network or an ensemble of deep neural network, right? They're universal function approximators. They're very easy to do, but of course they're much slower, right? Because these networks usually require large widths and large steps. So if you want to use this in a real-time setting, it's probably not going to be as fast. Well, if instead you use something as, I don't know, something like a dynamical system or, I don't know, basis functions, they're not as expressive, as in like the set of dynamics that they can learn or they can express is probably going to be much less than the set of dynamics that a deep neural network can express. So there's usually a trade-off.
Okay, got it now. Yeah. That's very interesting. It's the exact same in music in terms of trading off expressivity of a system for real time. So it's kind of amazing.
Well, I did not know that. Hi, Braden.
Hey, Josue. Just to I can't remember if I've asked this question before when you've talked about this, but I was just curious. So here you have the exploration problem, but of course in foraging type tasks, there's this exploration exploitation type trade-off where there could be resources or rewards in this case distributed throughout the environment. So I was just curious if you've explored this sort of trade-off with the escape the maze model, where in something like the maze or some other dynamical system, there are also just rewards in the environment that the agent could pick up, and it has to sort of determine when it should stop exploring and just exploit its current location, and if that's just a free parameter in the model, or if it would sort of naturally find this balance.
Yeah, so from what I'm aware of and from what I've seen, it's usually a free parameter. So what I've seen, what people usually do is like they either take the reward signal RFT from the environment, and they just augment the intrinsic reward signal, and they weigh that thing by some hyperparameter beta. And so that thing would then determine this, right? If beta was super small, then the agent would be really focused on just getting like this exploratory rewards, while if it was super large, and it would really focus much on exploration first. And so I don't know of a way to naturally do this. So I won't lie, but that's the way that I'm familiar with. And I mean, I have been meaning on seeing how this would do compared to all these other methods in an actual task as opposed to just fully exploring. I should probably do it. I will do it. is my answer. I will do it.
I mean, it sounds like an even harder task than what you've already coded up. I was just curious. Thank you for the answer.
Hi, Kurt.
Hey, so I want to ask a potentially unreasonable question, but I'm curious to know, do you have any thoughts about implementing an escape the maze type algorithm in environments with time varying dynamics? Like, is this something you've thought about at all?
Yeah. So one other thing that I've kind of swept under the rug is this will be slightly long-winded, but I'm going to say it anyway because I think this is cool. But okay, so here we're using an ensemble of deep neural networks, right? So there's actually a lot of reasons why we do this practically. The first thing is that like the hyperparameters don't matter as much if I were to use a GP, for instance, right? So since I'm doing online gradient descent, right, it always, I mean, it's going to find the weights that are going to do the job. And as a byproduct, what you would expect, hopefully, is that if you were in an environment where the dynamics are changing at least somewhat slowly, right, not changing, like it's not an instantaneous jump, but if they're somewhat drifting slowly, then because we're doing online gradient descent, it should be able to track it at least decently well. I'm not going to say anything beyond that. But here I did mention that you could also use a Bayesian approach too. The other actually nice thing about the ensemble deep neural networks or non-Bayesian approaches, or Bayesian approaches with quotation marks, which I still think is I'm going to go with, is that you can actually show that regular Bayesian approaches are actually not well suited for this problem. I mean, you can talk about this offline, but what you can show is that if you just use a naive GP, for instance, and you just keep on collecting data from the environment, there's actually two things that suck. The first thing is that in like regular GPs, right, your uncertainty always decreases with the data, regardless of where the data comes from, which means the learning speed also decreases. So actually, regular Bayes for non-stationary environments is really bad, actually. Horrible. Tremendously bad, actually. Tremendously bad. And so I do have some work with this with some friends of mine, but it's not on a preprint. So you just have to believe me. Or I can send it to you offline. But yeah, so that's the other nice thing about using an ensemble of deep neural networks. But so there is somewhat of a, I guess there is somewhat of a trade-off. I mean, if we were to apply this in a real-time setting, I guess we do want to do something that does gradient descent, but the uncertainty is not principled. Yeah, I guess there's a trade-off, but long-winded answer, I apologize. I hope that I answered your question at least somewhat.
No, it was awesome. This is all interesting stuff. Maybe we could talk offline.
Thanks, Kurt. I can't tell if Giancarlo's going to ask a question or not because he's unmuted.
So another question, the dimensionality challenge, what's the path forward on that? Or do you basically, you're always anticipating having to find some subspace in which you can...
Yeah, so we're kind of assuming that for the problems that we're focused on, that the space is pretty low D. So I mean, one thing that's commonly done is if for example, X is high D, then we could learn like some latent variable model, which is the next step forward. So even though the observations are high D, it may actually live on some low D manifold. So if we learn this latent variable model, which is a much lower dimension, then we can keep landmarks there. But really, I guess the only way to go forward is to either do some sort of projection scheme and keep the landmarks in this low D space, whether it's through projection or through latent variable model. But yeah, this method just is not well suited for like exploration in just a high dimensional space. It's just way too hard.
Okay, thank you.
All right, I guess we have perfect timing. It's 1 o'clock.
Oh, sweet.
If there's no other questions, thank you, Josue, and thank you everybody for